we are about to begin. Next, I'm passing the word to Dr. Giselle Montserrat Galvan Tejeda, Head of the Department of Electric Engineering here at Simvestab.
Morning, everyone. Dear colleagues, professors, students, and assistants, it's my pleasure to give you a warm welcome to the 22nd International Conference on Electrical Engineering, Computing Science, and Automatic Control, CCE. Let me introduce some single words to open this conference. This year, our conference celebrates 30 years of the first International Conference on Electrical Engineering, CIE 1999, organized by the Department of Electrical Engineering of the Center for Research and Advanced Studies, CINVESTA, which later evolved to an international conference where we are happy now met. As a part of this evolution, CCE is organized in a hybrid modality. So there will be two components of participations, in person and online presentations. The conference remains as specialized forums where local and international research groups can present the recent research results and proposals, interact each other, and they can become aware of recent research and development from leading institutions. The interaction with technological industry keeps a special place in the activities of the conference. In this 2025 edition of the CCE, we initiate the activities with one of three plenary talks given by recognized researchers from IEEE. Dr. Charvaka Duvvury from ESD Consulting LCC Texas, USA, to whom thanks his participations with the talks Advanced Electrostatic Discharge Technology Issues. Welcome to Mexico City, and the Department of Electrical Engineering of CINVESTA. Tomorrow, Dr. Banyan Li, Professor of Medical School from Shenzhen University, China, will give the talk Empowering Medical Image Analysis and Artificial Intelligence. Friday, Dr. Ji Huang, Professor of the Department of Electrical Engineering and Electronics from the University of Liverpool, UK, will share with us the conference wireless charging for medical, EV, and IoT applications. Additionally, through these conference days, authors will expose their contribution on all areas of the CCE: automatic control, biomedical engineering, communication systems, computer science and computer engineering, mechatronics, nanotechnology, power electronics, solid-state materials, electronic devices, and integrated circuits, aeronautics and aerospace engineering, autonomous navigation, and mechanical engineering. Enjoy all of them. So please join me to give a warm welcome to Dr. Duvvury, and I give the word to Dr. Arely Cano to introduce Dr. Duvvury and moderate the sessions. Thanks a lot, Doctor.
Okay, good morning and welcome everyone to the 22nd edition of the CCE conference. So it's great to see everyone here in person in 2025. And also it's great to welcome all of you who is joining us online via stream for this inaugural lecture. So my name is Arely Cano. I'm a researcher here at the Electrical Engineering Department. And today it's my pleasure to introduce our first keynote speaker, Dr. Charvaka Duvvury. So sorry if I'm not correctly pronouncing correctly your name. So, but before that, let me read a few or say a few words about his career. So Dr. Duvvury earned his PhD in engineering science from the University of Toledo and completed postdoctoral work in physics at the University of Alberta before joining Texas Instruments in 1977, where he spent 35 years pioneering the ESD design methodologies. He was named PI Fellow in 1997 and IEEE Fellow in 2008. So Dr. Duvvury has been instrumental in shaping industry standards for IC reliability, serving on the board of the director of the ESD Association since 1997 and co-founded the Industry Council on ESD in 2006. He was twice chair the EOS ESD Symposium and continues to promote the ESD education across industry and academia. His contributions have been widely recognized through multiple prestigious awards, including the IEEE ESD Education Award in 2013, the EOS ESD Outstanding Contribution Award, and two Semiconductor Research Council Outstanding Industry Mentor Awards. So he currently works as a consultant to the semiconductor industry and is a co-founder of the IT2 Technologies, which is advanced software-based solution for rapid ESD data analysis. So without further details, so please join me in giving a warm welcome to our keynote speaker, Dr. Charvaka Duvvury. So Doctor, the floor is yours.
Yeah. Okay. Okay.
Yeah.
Okay.
Okay. Buenos dias. Uh, I'm very happy to be in Mexico. It's a beautiful country, and we have many cultures of Mexico. Where I come from Texas, is a lot of Mexican food everywhere in Texas. So everything is very familiar to us here, and it's very nice. And Mexico City is very beautiful. I would like to talk today on electrostatic discharge. This is a subject that became aware to the industry only 50 years ago, just about 50 years ago. Um, it is becoming more and more important, and there are now hundreds of researchers all over the world on this topic, because the more advanced is the technology, the more difficult it is to protect against the static charges. So I will try to give you an overview of ESD and then followed by some of the issues that we are facing. I would like to mention that the IEEE EDS has sponsored this presentation, and as you probably are all aware, it's a very important organization of the IEEE, and they promote excellence everywhere. And there are a lot of different topics in IEEE that are very important to branch of electrical engineering. And there is also what they do are education, publications, networks, and projects, friendships, and ideas. It's a worldwide organization. And so IEEE, if you're not a member, they encourage everyone to become member of IEEE. Okay, so let me talk with my presentation. I'll first go back 50 million years ago, and there was the comet that struck the Earth, and there was nothing on this planet. When the comet struck the Earth, there is nothing but dust everywhere. There is so much dust everywhere that you have lightning. There was so much lightning all over the world that the only creatures that were alive were the dinosaurs. 50 million years ago. So what we think is that all that lightning has pretty much killed all the dinosaurs. They fell down and they killed the smaller animals, and there was all this destruction probably happened because of ESD. So they didn't have any lightning rods. If there were lightning rods, they would all been protected. So this is the idea of ESD. ESD is very much applies to semiconductor devices, that it is a lightning that does happen, and you need to build little lightning rods on the IC chips to protect against the ESD. I'm sure that you are all familiar with the painting of Michelangelo. That probably was the first ESD pulse between a touch between two fingers is what, if there are two different potentials, then there is a discharge between the two fingers. So this is what is of concern for us, is the electrostatic discharge. Now, why is it important? It is important because for biomedical chips, automotive sensors, aerospace satellites, wireless communications, all of them are affected by ESD. So ESD stands for electrostatic discharge. The first time that in the early to late 70s, when people became aware of ESD, at that time, many of the managers and semiconductor companies, they really didn't believe in ESD. They thought ESD stands for evil spirited devices. There's something evil about it. They didn't really believe it. They actually had to take the managers into the, show them, charge up human beings, touch IC pins, and show the damage that the diodes in the IC circuits have been damaged. So then only they started believing. So what I'm trying to say is 50 years ago, nobody even took it seriously about ESD. So in this talk, I will give you a background. How is ESD modeled, and how do you protect? And then the advanced technologies, and then we enter the high-speed IOs and system level issues. That is not ESD, is not only on the chip level, but at the computer level, you need to protect whole system. And there is another concept called electrical overstress, which is different from ESD, but is equally important. So I'll briefly mention that and some of the new technologies and research opportunities in this topic. One nice thing about ESD is that there is a great opportunity for many patents. People generate a lot of patents. There are now thousands of patents on how to protect the IC chips. There is another advantage is that any student who works in ESD pretty much guaranteed a job. Is because it is so important and so few people are working on it. Anyone who works in it becomes a specialist in the topic. So let's talk about this. ESD is when you touch a doorknob in winter, the static discharge from your finger to the doorknob. ESD is something that is always present around us. Human touch on IC devices can result in damage. ICs placed in circuit boards can also see ESD damage. Circuit boards in electronic systems can fail due to ESD. Without proper protection, then systems fail to operate. So that's the reason ESD needs a constant attention. If nobody took care of ESD for the last 30, 40 years, many semiconductor chips would not have been manufactured. So that is the importance of the topic. So ESD is what is around us each day. Every day there is ESD all around you. It's pervasive and can damage IC devices during handling, assembly, shipping, and testing, all these different areas. It can cause destruction of electronic devices in automotive, medical, military, and consumer applications. ESD can be controlled and protection designs are important. This is where the job is available to many of the electronics, electrical engineering, how to protect these chips with a device design or a circuit design. Besides ESD, there is electrical overstress resulting from exceeding the specs of voltage and current can also cause damage. What I mean is that if a part is specified as 3.3 volts on VDD, you don't apply 7 volts on it. If you apply that, you can have severe damage of the device. So at one time at Texas Instruments, when we worked, we had ICs that were specified with 3.3 volts VDD, and many of them started coming back from one customer. And we asked the customer, what were you doing? They said, well, we're applying 7 volts. Why were you applying 7 volts? Because they said it runs faster. Yeah, it runs faster, but it's going to damage the chip. So that's why electrical overstress is important. So industry needs to understand the nature of this, the physics, and then design the protection for it. So if you look at the typical failures of IC production, you have ESD, EOS, fabrication, unknown, assembly, other, and mobile ions, a lot of different reasons why semiconductor devices fail. But the major one of them are ESD, EOS is the major cause of failure. Now, out of these, only 3% are ESD, 97% of electrical overstress. So you would be wondering then, why are you worried about ESD if it is only 3%? The reason is, if you don't do anything about ESD, it will become 90% of the failures. That's the reason it's 3%. It is because everyone knows how to control it, how to protect for it. Now, on the other, electrical overstress, you can help it. It all depends on the customer. What are they applying? So that's a very different field. And then if customers are taught properly how to apply the voltages and currents on the devices, then you will not have electrical overstress. So that is the distinction between the two. So let's look at ESD from lightning to ESD. ESD itself is only about 1 volt to 15,000 volts. It's high voltage. It's less than a microsecond in duration. It's a very short rise time of 10 nanoseconds, and it's very low power. So on the other hand, electrical overstress is low voltage, is much longer in duration and low power, and lightning is extremely high voltage and extremely high power. So those are the different things. So IC devices in automotive, medical, all of these need ESD protection, whereas houses, buildings, airplanes, and electronic devices need surge protection and lightning rods, all of that you protect. So we are now going to focus on ESD. That is the topic of this presentation. So the next question is, how is ESD encountered? Humans develop environmental charge stored with human body capacitance, about 100 puff typical, but depends on the mass, temperature, and humidity. So the 100 puff is the average capacitance of a human being standing on a floor, okay? Big people have more capacitance, little people have little capacitance. But now they took it as the average capacitance as 100 puff capacitance. So the humidity will make a lot of difference. If it is dry environment, you'll get more static charges. And in a very humid environment, it will be less. But we are talking about a production area where the humidity is controlled to 45%. That's the ideal way of handling all the devices with humans of about 100 puff capacitance. Humans, when interacting with electronic devices like cell phones, touch screen, their body capacitance is uh, sensitive, causing VSD events. Now, the charge can be stored or accumulated across physical bodies when isolated from ground. So you see the hand coming, a person that is charged, coming close to an IC device, which is at the grounded potential, the pins, then you see the discharge, the corona discharge from the finger. So that's the reason you have to make sure that humans handling the devices are protected. If you don't protect, you can have a pretty bad thermal damage inside the transistor. So this is the first indication to people, okay, we need to understand it. Now, humans can be charged to any voltage. Regularly, in regular life, you can be charged to 4,000, 8,000 volts. And when you're charged to 8,000 volts or 10,000 volts, when you touch any doorknob, you can sense the thing. You will get a little shock. But humans who are charged to 2,000 volts, they can't feel anything. But you don't feel anything. But the IC device gets damaged. Okay. Now, we address only in a production area where everything is controlled. Even when you control everything in a production area, the humans who are working in the production area can be charged up to 1,000 volts. So that's the reason we say all the IC pins must be protected to 2,000 volts to give it a margin. So if you control all the production areas to 1,000 volts, and you protect all the chips to at least 2,000 volts, everything is fine. And now, when the IC goes out into a printer circuit board, into a system, there is no control. Anybody is doing anything with, and that's the reason you protect the system. That's very different from protecting the IC chip. So again, you first protect the IC chip. Once the IC chip goes into the external world, it's a different concept. ICs can be human body, a machine, or electronic equipment. And ESD is the transfer of charge between bodies at different potentials. And so even when an IC is coming through a handler, it gets triboelectrically charged because in a plastic tube. And when it hits a ground plane, you will get a little discharge right there. So instead of humans, packages themselves can get charged, and especially if you are a robotic arm is probing, that there could be a discharge from it, or in a socket, devices placed in a socket. So there are many different forms of this discharge that happens. The two important forms are, one is the human body model, that is you as a person touching the device, or contact from machine to an IC. That's a different kind of model. So that is called the charge device model. The device itself is charged. So those are the two models that if you can model those pulses, then you know how to protect those pulses. Okay, if you usually for the charge device model, you usually get a gate oxide damage, as you can see. Where the human body model, you can get a junction damage in a transistor, or gate oxide with the charge device model. I will explain that in a minute, why the difference between the two. There are actually different kind of damages: charge device, human body model. And the third one is called an IEC, International Electrotechnical Commission, has said that when the devices are outside the production area, they can get much higher zaps. And if you don't protect them for that, you will get very severe damage that you can see here. So the human model is the most important one. As you can see, is 100 puff capacitance. But fortunately, the human finger resistance is about 1,500 ohms. If you don't have any resistance, we would all been killed. The current would be so high, right? It's the resistance that is protecting the human beings, especially. So even if a human being is charged to 2000 volts through a 1500 ohm resistor, you will not get much current other than 1.3 amps current. But that too, that current discharges, decays because of the capacitance and resistor with a time constant. So this energy under the pulse is what causes damage to the IC devices. So that's what we're trying to do, protect for that energy under the pulse. Okay, that energy, as I said, is only microjoules. You don't feel anything at 2000 volts, but the IC devices get damaged. Oh, by the way, if there is as I said, if higher the capacitance, bigger the human being, higher is the capacitance. I used to joke with my friends in Germany, there should be 200 pop rather than 100 pop. People who drink a lot of beer have even more capacitance. Okay, and also, as I said, that the 1500 ohms is something we should be thankful. Maybe one day there will be aliens coming down to Earth and they don't have any blood. They probably have mercury in their veins and they have zero resistance. Then that will be pretty dangerous, any alien touching these devices. On the other hand, charge device model is more difficult to model because it's not a human. There are 400 varieties of packages in the industry. So each package, small package to large package, the capacitance is completely different. So even if they're charged to the same voltage, a bigger package causes more damage than a little package. So how do you test for it? One way they test for it is they induce a field on the IC chip, charge the device to a few hundred volts, and discharge it through a robotic arm. When you do that, what you get is a very high, very short rise time, less than a nanosecond in width, 200 to 300 picoseconds in rise time, about 10 amps or so current. So you see, it's a very narrow pulse with a high current, but the energy is not very much. But the thing that causes damage is the very fast rise time. What happens is suddenly, if there is even 2 ohms of resistance in a line, 10 amps at 2 ohms is 20 volts instantaneously. And that causes the gate oxide to be damaged. That's why the charge device model, you see the damage in the gate. Whereas the human body model, the damage is a thermal damage. Usually, packages don't charge up to thousands of volts. They only charge up to a few hundred volts. So you do that only about a few hundred volts of operation on those. And it's completely package independent. So you have to protect in a different way, depending on the packages you are dealing with. So those are the two models. Now, what about pins that are not on the IC pin? What about if there are pins that are external interfaces like HDMI or USB? Those pins can also get ESD pulse. When they do that, only the pins that are outside interface are the ones that will get damaged. Now there, it's not 1000 volts, it's 8000 volts or 12,000 volts, a lot of, so very different type of protection has to be done for these pins. So the model for that is about 150 pop and only 330 ohm resistance. Now this is a model for a human metal model. It is like if you're taking a screwdriver and touching in the back of the your computer or anything, you can get a lot more current. Your finger resistance is not involved. Okay, so that is the International Electrotechnical Commission has come up with this model. There, the pulse is very, very high. See, the current pulses are 30 amps or so. Sorry. Thing. Yeah, you notice that it is much higher current, but it's about 50 nanoseconds. So if you look at the models now, the human is about 150 nanoseconds, about 1 to 2 amps. The package is tens of amps, very narrow pulse, and a system when like people touching in the back of the computer can be much. So it's a much bigger pulse and it's a lot more energy. So what we can do is look at the logarithm of power versus logarithm of time. And you notice that this is the famous Wunsch-Bell model, which has been modified by Dreyer. Even in 1990, he has modified this. That is, first it's adiabatic, then it's 1 over square root of t, then it's 1 over logarithm of t, and then there is constant power. So here we are plotting the pulse width and the failure power. And if you notice this, what this is, if you look at the ESD damage, the human body model, first the CDM, the charge device model, is in this time range. And then the human body model is in this time range. Now notice the dependence is 1 over square. And there is bring computer, then that is charged too. So you see, just all these operations in an electronics environment causes a lot of discharge that can cause damage. So all the internal pins need to be protected for that human body and charge device. External pins for this interface pins require a special kind of protection. And then the on-chip ESD protection is not applicable to any of the other events. So on a chip, you can only protect the human body model and the charge device model. On the interfaces, you need a different approach. So basic HBM CDM covered the IC pins, how to handle external pulses on interface pins like USB and HDMI require a different strategy. Now let's look at all the different waveforms in one time scale to see if we can see everything. Here we're plotting the current and we're plotting the time but this is broken here because it's 100 nanosecond to 1 microsecond to 1 millisecond. So, okay, so now you can see that's what the human body model looks like. A low current, long time. And then the charge device model is a very short pulse, higher current, but right there. And the next one is the cable discharge. Now it's longer and more energy. Okay. Although lower current, but still has a lot of energy. Now the electrical system level event like the International Electrotechnical Commission IEC, even at 8 kV, it is a lot of power. So that's why the difference is. Whereas electrical overstress, there is no pulse width on it. It's just a long time of voltage. So those are the different mechanisms that do happen. So how do we handle devices? Okay, first, in the factory, you have to make sure all the operators are fully protected. So what you do is you ground the person to make sure the person is at minimum voltage. Then you also ground the work surfaces. So as shown here, work surfaces are grounded. And then ESD protective packaging, this almost look like some cocaine bags, but actually those are materials with anti-static materials, and they're packed and then shipped to the across. And so those are the three different precautions. If you don't do any of these, there won't be any electronic devices. So how do we deal with all these different forms of protection? You need to look at, it's not just the device. ESD happens even in the fab area. In the fab area, you have any kind of long metal line or long poly line acts like an antenna, and it can accumulate charges, and then it can damage the vapor itself. So you have to put diodes to protect those. And also you use air ionizers and static handling methods. Otherwise, even when the vapor is spinning, water jet can damage the gate oxide. So that's why in the fab area, it's important to protect. Then in the assembly area, you have ionization grounding, and this is where we do the protection on the IC pins itself. Then once it goes into the system, printed circuit board and assembly, you need a very different kind of system level protection. That's the system level. And then the case grounding and protection, that shielding and ground pins. So the end customer. So when you look at your laptop, in the back, there is a shell around it that's to make sure you don't accidentally touch any of the pins. So the shell is a grounding shell. So all these precautions are done to get the entire IC protected. So this is called the ESD protected areas. So whatever you're designing, you only protect here. Once it goes outside into ESD exposed areas, it's a different kind of strategy. So how do you protect these chips? If you have a IO pad, then you have the input buffer or the output buffer. At the input buffer, you put an ESD clamp to VDD and to VSS. So when there is an ESD pulse, the ESD device turns on and takes all the current away. And it should be designed in such a way the operation of the IO is not at all affected. Okay, so ESD device is like a switch, turns on and turns off, and you shouldn't have anything to do with the rest of the circuit. The same way you can put it on the output buffer also. That's how the protection is done. ESD clamps are designed to protect the buffers. ESD clamps are designed to protect output buffer drain junctions, the input buffer gate oxide, because it's the gate oxide that you're interfacing. These two are important. Must have low impedance to prevent voltage buildup, and must have low impedance to prevent any kind of secondary current into the device. So these are the issues of protecting the devices. How to protect, turn on, turn off, not bother with the IO operation. Okay. Most of you know the MOS device. So what about using the MOS device to protect for ESD? If you look at the MOS device, It's just surface current drain to source current, and the IV are linear and saturation. Then once you exceed a certain voltage, it will start, the junction starts to avalanche. That's the avalanche region. The circuit designers only deal here. They don't care anything about what happens outside the application voltage. But ESD is outside the region. Okay? So transistor with any kind of bias on the gate would conduct drain to source current, and is useful for circuit design, linear to saturation, or model with SPICE. So that's the MOS device. And then at higher drain voltage, the drain junction avalanche is leading to breakdown. This is the high current region. The whole idea is ESD is a high current region physics, different from the MOS device, which is a lower current region. So what happens, the drive current that you get drain to source is not enough to handle the ESD device. ESD device currents are in the amps of current. So you can't use a MOS device to protect for ESD. So what happens now, if I now tie the gate of the MOS device to the source, now the gate is grounded, so there could be no current, no drain current. Then what happens is the device characteristics will avalanche, break down, and go like this. That is like becomes a bipolar device. A MOS device can operate like a bipolar device. In the sense, it goes into snapback and then it goes into bipolar conduction. So what's the advantage of bipolar conduction? It can take more current than a surface conduction. So 10 times more current you can get. So that means a parasitic bipolar device can protect for ESD, whereas the regular MOS is operated as a MOS device. That is the reason that it is modeled like this. The drain as a collector, the substrate as the base, and the source as the emitter. So the NPN conduction of the device itself is the ESD protection that can be formed by grounding the gate. So that's one simple way of doing this, is this protection. The parasitic NPN is used for ESD protection devices. So if a MOS device can handle 1 microamp for micron width of device, a ESD device can handle tens of amps, milliamps per micron. So it's much higher in these. So how do you characterize the MOS device? How you are trying to protect human body model. You already know 100 pop capacitance and 1500 ohm resistance. So how do you model that? The way to model that is if you can generate a transmission line pulse, like a 50 ohm cable charged to high voltage, and then discharged through a matching 50 ohm, then you can get a 100 nanosecond pulse with square pulse, current pulse. That 100 nanosecond square pulse is approximately equivalent to the human body model of 150 nanosecond decaying, same energy as the two. So now I have an instrument. I can measure the devices, characterize the devices to see how well they work for ESD. So when I use the transmission line, you notice the current versus voltage. I keep increasing the voltage till I see the device go into bipolar conduction. And you can see once this reaches certain voltage, it snaps back. And then it goes, and you keep increasing the voltage, the current increases, and there is a little on resistance, and then it gets into a thermal region of damage. So if I can measure, if I have a 100 micron wide device, how much current can it handle for ESD? Then I can design or say, okay, I need 400 microns wide to handle 2 amps of current. Okay, that's how the design is done on the devices. So all these trigger points are all involved, and they are very, very dependent on the physics of the device. a lot of junction damage. All of the junction characteristics are dependent. It's a lot more complicated physics, but this is the basic idea. Because in the technology, if you keep changing the transistor junctions, all these parameters are affected. So that's the challenge for the engineers to, so using the transmission line pulse, you characterize a lot of different technologies. One thing I forgot to mention here is that this can also be modeled to handle 1 to nanosecond pulses for CDM energy also. So now the designers have all the tools, the TLP for understanding human body model, the very fast TLP to understand the charge device model. The devices, there are many fundamental devices. These are PN diodes for clamping voltages, MOS devices working as parasitic devices with the gate grounded, MOS devices operating in full MOS conduction. You can also use that, although I didn't show it here, I'll show later. You can use a very big MOS device to handle the ESD current too. But such a big device is not practical at the IO pin. But you can take a large MOS device, put between VDD and ground, and you can handle a lot of current that way also. And then silicon controlled rectifiers as a PNPN devices, or diffusion resistors as current limiters, polysilicon resistors as current limiters. So these are all the ones in a toolbox that the designer characterizes everything with a TLP or a VFTLP, then knows how these devices operate and then formulate the protection devices that way. Everyone knows fundamentals of a PN diode, anode and a cathode, and the current turns on. This is 20 to 25 milliamps for each micron parameter, a typical value. So a reasonable diode can handle a lot of current, of ESD current. So that's a forward bias diode. But if you have a reverse bias diode, if you switch the anode and cathode, the breakdown will be the junction breakdown, which is much higher, 7, and the resistance is much higher. So this is not very good for ESD, but it can be a blocking diode. If you want to block conduction in one thing, you use a reverse diode. Then as you saw, MOS devices that we showed here can handle much higher current levels, and they trigger at a different voltage. And then if you, as I said, the physics is quite involved in modeling these for thermal TCAD modeling that you can do, understand how they operate. This is the avalanche. This is the first breakdown. This is the bipolar conduction. This is the filamentary conduction. And you monitor the leakage of these devices. And suddenly when there is a thermal damage, you notice suddenly the leakage jumps. This is how you know what's happening in the device. Here you can have tunneling, band-to-band impact ionization. And here, second snapback with bipolar is a negative differential equation. Notice that the voltage drops. So that's a negative differential conduction. Then there is the thermally induced instability that happens here. That's why the leakage is fluctuating. And then eventually the device gets damaged. Now the same MOS devices with a substrate makes a difference. If it is a bulk substrate, it's very efficient. But if you put it on an SOI, on the other hand, it's not as efficient because, see, the oxide here is preventing the heat from going to the substrate. So as a result, SOI is less efficient for ESD performance. So there are a lot of things that are involved in ESD design, how to get the heat from here into the substrate, or can I make a substrate correction somewhere in an SOI technology to get the heat back up. So the whole idea of ESD is not let the current stay at the surface, bring it down, cooling it down, then you can design the protection devices. There is also what is called a PNPN device. That is, if you have the P and N in a N well, and you, at the border of the N well, you put another diffusion and another gate diffusion grounded. This is a grounded gate device. And when this triggers, then you will have a vertical PNP and a lateral NPN, and that's what we call a semiconductor rectifier or an SCR. And with that, you can handle even more current, see 30 to 40 milliamps. So higher the current a device can handle, the better it is for ESD. So the SCRs are also very powerful protection device. The only danger of an SCR is if they latch up, they go to much lower voltage and can cause a latch up in the circuit. So you design so that the latch up and ESD are all balanced together. So in forming the protection devices, you have the IO pads here, and then you build a second stage here so that there is a local clamps so that you put a resistor in between. So even though ESD device turns on, it can still go to 10, 15 volts at this point, and you don't want the gate oxide to break down. So you create a voltage drop to put a smaller devices, and that will be the thing. So the primary device and the secondary device with the resistor in between, that forms the protection. And then secondary devices are small diodes you can place. These are all important for protecting the total chip. Now, in a total chip, it's not just one VDD. If you have different VDD, high voltage, low voltage, all these different things, then they are in different buffers like this. And if they're in different buffers, you have to make sure that the ESD current goes through each one of them. And you can put large clamps, MOS devices between VDD and VSS. So each IO cell, the current goes through, comes here, goes through, come here, goes through, and come here. So you can do these techniques. And on the other hand, these are blocking diodes. So you can put an NPN device, SCR device, diodes, any design that you use, and people use different methods to protect these devices. So basically, there are two different approaches. One is you put a clamp local at the IO pad, so current will only go this way, or you put a diode to the power supply and let the current go through here. And you put a 3-stage inverter stage here with a resistor and capacitor so that the MOS device will turn on only during ESD and then shut off. So now you see the second approach. This approach is more useful for advanced technologies. The reason is this MOS device will introduce capacitance. That even one pop of capacitance is very, very intolerant for high-speed IOs. So if you want to avoid that capacitance, then what you do is you replace this with a blocking diode and let all the current go through the power pin. So these are all the different things. Although these are all look very simple, everything is quite complex because there is a lot of noise on the VDD. You don't want that device to turn on for any other application, that is slew rates and so on. So if you have different power supplies or different designs of low voltage VDD, analog, and all of these have to be coupled together with diodes. Otherwise, you will have. So notice that everything is coupled by diodes, all the grounds, so that everything is protected for all different combination of pulses. So advanced technologies. ESD is only one wheel of the technology, okay? You have electromigration, electrical overstress, latch up, channel hot carrier, negative bias, temperature instability, oxide quality, corrosion, contact, and via. All of these things play a role in the semiconductor technology in the sense that they are related to somewhat in ESD, in the sense that electromigration, there if you have a metal line that you're using for ESD, and if it heats up during ESD pulse and then cools down, you change the grain boundary, and then you change the resistance of that metal, then it can have an impact on the electromigration lifetime of that device. So you see that every one of them has some interaction with ESD. Same way, the most important of all of these is the oxide. Oxide quality is very, very important. Even small ESD pulses can damage the oxide. You don't even know you damage the oxide. Then can reduce the lifetime of the oxide. That's the reason the charge device model is so big. Or corrosion. If there is a bad process with corrosion, you have more ESD problem. And contacts. So these contacts and vias have to handle ESD current. If you just put one contact for an ESD device, it can't handle all that current. That's why people put 20 different contacts in parallel so current is distributed. Otherwise, you will get an electrothermal migration of the contact into silicon. So you see the physics is more involved in these devices. And what do we mean by advanced technologies? They require basic understanding of high current physics and allow using protection elements such as MOS, diodes, and so on. And then advanced ESD means having to understand the change in physics. When you scale down technology, the physics is changing. And so now it becomes more challenging. It also means compatibility between ESD and IO design. Different operations. Advanced ESD requires meeting protection design for also RF applications. So now things are becoming more and more complex as you have different IO design technologies. And then in addition, you have on-chip protection, compatibility to external like USB and HDMI. So what do you monitor when you look for ESD characterization? You monitor the junction avalanche voltage, you monitor the oxide reliability, you monitor the metal oxide current density. If you understand all of these, then you understand your window of how you design for ESD. For example, there is the window that it operates, the VDD and the breakdown voltage. So, and there is a thermal failure on the top. And so you don't want the ESD device enter the breakdown device. You don't want the ESD device to clamp below VDD. And you don't want, if you have a ESD target that you're meeting, you don't want to go to the thermal failure. So that's the window that you operate. So as the technology is advanced, what is happening is oxide is breaking down earlier voltage, and the heat capacity of the metal lines is reducing. So the window is closing and closing and closing. So that's the reason ESD device challenges. So technology scaling, you have, if you look at the year of the calendar and the technology node and how well it does for ESD or the lightly drop drain junctions, they are done to counter the channel hot carrier. They have an impact. They started at 2 micron and they started having a problem for ESD already. Then you introduce silicide diffusions and that makes it even worse. The conduction is not so uniform, silicide melts, and it's problematic for ESD. Then you have gate length reduced, so the channel heating increases as you make smaller channels. And then you have strain engineering, and then you have ultra-thin gate oxide with high-K dielectrics, and then FinFETs and much more local heating, local scaling effect. So you can see that the ESD performance is going down and down and down as you go in technologies. Even if you use a diode, a standard diode, there is a current that goes from P to N that it itself can have a problem during CDM in the sense that the current can go up not as, not as efficient because of longer path. But what if I block this path? For example, I put a gate, dummy gate, and notice how much more current it increases. So even the diodes, a diode is not just a diode. A diode is very complex in design. We used to joke with a guy that had 50 patents on one diode. Every little layout change, he claimed a patent on it. So even a diode is not just a diode. And then under CDM also, the current path can increase the voltage locally to the oxide. So there is an overshoot in the diode. A diode doesn't turn on immediately. There is a time it takes to turn on. By that time, the oxide might be damaged. So if you put a dummy gate, then the transient pulse, the overshoot is reduced. So these are some of the techniques that people use. Then, of course, the high-speed IOs, if you put all these here, any kind of resistor here has an impact on IO speed performance. So the worst is you try to minimize this R to see how fast the IO can perform. That is, you have to understand in the diode about conductivity modulation, reverse breakdown, voltage overshoot. All of these are important in trying to design for ESD. And the higher the capacitance, the better it is for bigger the device, but you cannot handle big devices. So you you make it smaller to be compatible with data rates, but then you don't get the HBM performance that you're trying to design. If you make smaller diodes, you will get lower performance. So now is it dangerous to have devices now with a lower HBM performance? And that's the reason we formed the Industry Council on ESD about in 2006. And we said that you really don't need 2000 volts of protection. The factories are so much sophisticated now, even 1000 volt of protection is good enough. And that will allow you to design for high-speed IOs. Otherwise, you can't be manufacturing high-speed IOs. So that's the thing. Like, for example, here, the charge device model protection versus the number of BGA pins on a device, the more BGA pins, the more capacitance, lower is the protection you can design for. And that depends on the technology and the gigabits per second. So that's why it's complicated as you go into more and more advanced technologies. So that's sum up here, the loading capacitance from an ESD device in femtofarads versus what kind of CDM protection you can achieve versus the data rates that we want to. We are now at these data rates. So that's why the CDM protection has dropped from 500 volts to 125. That means the factories have to be even more sophisticated in handling these very, very sensitive devices. And the RF is a big problem too, because if you put any kind of ESD device, the figure of merit for the RF drops down. You can't get that same RF performance. So a lot of techniques are involved in understanding RF and ESD. There has to be design space that is shared between RF and ESD cell as part of the total functionality. So now you understand that high-speed IOs, you cannot design for high ESD levels. RF, you cannot design for high ESD levels. So the thing is, because you don't want ESD device to compromise the performance, noise gain, any of the performance of an RF circuit. So that's why there is a whole field of RF ESD. Many designers and engineers are involved in making sure RF antennas, RF circuits are protected for ESD, but not compromise any performance. Now, I want to briefly mention about system level ESD. A system is a complete unit, module, or a subsystem. The purpose of ESD testing electronics and electronically controlled product is to ensure survivability. You want your laptop to operate, you want your mobile phone to operate. Because one time I was sitting next to someone on a plane and they were polishing the phone on their sweater. And that's horrifying to see because you're putting so much system ESD into the phone. So the phone designers have to make sure people do all kinds of things with their phones. You cannot control people what they do. And so the idea is to make sure these phones are completely safe for any kind of ESD operation. So people do, as I said, crazy things. They put a screwdriver in the back of the computer or bump their chair onto the computer table. This is electromagnetic interference or ESD directly into the system. All of these things have to be taken care of under ESD methods. As I said, that you have to put the external pins, you need some Zener diodes to protect them so that any external pulse is clamped right here. It doesn't go to the IC pin. Internal pins are all protected with HBM, CDM that we talked about. So you have IC chip for chip protection, and you have performance, ultra high speed. ICs in circuit boards and integration and signal integrity. And then circuit boards in electronic systems, reliability and internet speed. These are all the things. Why do we need more and more high-speed microprocessors? Do you know why we all need? Because everybody is impatient. Nobody wants to wait for 2 minutes to download a picture. They want everything to be done instantly. So you have microprocessors now operating such high speed that you cannot put big ESD protection to get them to operate. That's the reason things become. Also on the system, it's an old phone. They don't look like that now. But you can have either a hardware or a software. This you can deal with. What happened? You can deal with it. You don't know what happened. The device has suddenly the screen became blank. Is it a real error, or do you have to reset the computer and it will be okay? So that's what you don't know. So what happens is, if you have a PC like here, there is my circuit design PCB circuit boards in there, and then you can suddenly get a software, or you can with a silicon diodes you can have protection, but they might. This is the eye diagram of a USB pin. You might be distorting the USB, so that is depending on the load of the diode that you're using. Now there are more advanced devices that you can do with an advanced diode. The whole idea is you want to preserve the signal integrity and still have ESD protection. This is another area that's very challenging for future. How do I maintain signal integrity and not have any ESD issues at all? So one thing I do want to say is, although you're protecting it externally, the voltage still goes up high here, and some of the current can just spill right through into the internal circuit. So you think you're protecting, but this can go. Zener has a resistance. So on a transient voltage suppressor, TVS, it can go to 60, 70 volts here. So depending on what you put in here, IC can see the damage. So this is what's called system efficient design. So when you're designing a system, you have to make sure your system clamp doesn't spill too much current into the IC pins. So they have to do different ways, like a phone chip, a mobile system, make sure that all the external events that take place on the antenna pin, on the connector pins, everything is properly controlled. So circuit board, like if you have a USB pin, transient voltage suppressor here, you put a common mode filter or a ferrite bead and capacitors and resistors, all these are placed so that the actual IC doesn't see any of the parts. Now, how do you know what is, so that requires a lot of modeling, simulations to understand how much energy is spilling in, right? And that's how you do the design. So is that when you look at the IC chip, if you don't have any protection, the energy is way too much. You can't put a protection device on the IC pin itself. It can't handle so much power. So what you do is you put in external protection so that the energy is diverted, only a little bit goes in. On the other hand, if depending on how you design, you can optimally design so that you can create a different current return paths so that uh, so that's the reason you can put a small protection on chip, take the major one with the external protection. This is what is about all current balancing, so that you want to make sure the devices and the circuit boards, everything is protected. As I mentioned, electrical overstress is when you go into this extreme region. And where this happen is it will suffer if you have exceed the voltage for voltage or current to the device. So this is the reason we spent about 4 years studying what causes electrical overstress. It's not just customer applying little high voltage. There are so many different causes. It will be mind-boggling. You see all the different region, unpowered handling, powered handling, say switching, AC operation, every little thing, this we call it a fish diagram, every little bone is a different reason for electrical overstress. So you get an idea, this is one area of research that is still a lot of work to be done. For example, even when in an automotive application, when you have the ECU, electrically controlled units that are plugged in, depends on whether one is charged, the other one is not charged. If it is charged, then you can have pulses that can damage the IC pins. So that's not the fault of ESD, it's the fault of the people who are connecting the electrical units together. And this is the reason we keep telling everyone, don't blame everything on ESD. It's also, there are different other reasons why things fail. The emerging technologies is that we went from CMOS, advanced CMOS, scale CMOS, 3-5 compound, gallium arsenide, gallium nitride, then FinFET, gate all around, emerging technologies like nanowires, nanotubes, 2D material, and 3D ICs. So you see now how fast that we are moving. All these require attention. FinFET, fully scaled silicon on insulator, lateral nanowires, vertical nanowires, monolithic 3D ICs, all need protection is because in a scale device, more self-heating, higher on resistance, lower intrinsic ESD, that is, even the failure current you measure under ESD is lower, so you can't design much. Gate oxides, very sensitive, scalable, scaling enables larger circuits, so big microprocessors become CDM a challenge. And then you have the 2.5D and 3D technology, that is, you have the super logic there is the interposer, the package substrate, and then memory stack. So all of these have to have these internal IOs that connect one to the other. You can, and this is where the local protections are needed. Otherwise, you are going to affect the high-speed operation of the IOs. So all of these require modeling as well. And then when you go into the fab areas, you are doing the micro bonding of chips, and then the die pickup, die transfer, flip again, and bond again. All of these are now having ESD, tiny ESD pulses. Nobody is able to monitor all this. So this is a whole area of trying to understand 3D ICs getting to ESD damage. And also there are advanced technologies like polymers. Maybe these are polymers are so highly conducting nano particles. Then if you can integrate into a polymer, it will look like an insulator. But under ESD, these little nanoparticles conduct and tunnel, and current goes through and they turn off. And this is the whole area of ESD that no one has explored fully. Polymer can offer very good protection. What's the advantage? The advantage is they can handle high current, turn on at almost a picosecond in speed, and then offer very little capacitance. So that is the future that needs to be done. Then there is graphene. There are few atomic layers, very high mobility conductors for internet, and high quality inductors. But the problem with the ESD is the high current density in thin atomic layers, so it can damage the graphene. In the same way, gallium nitride is a wonderful technology, high electron mobility for high power RF applications, and challenges for ESD include novel failure mechanisms. People really don't understand all the different failures that happen in the gallium nitride. So that is a whole, like University of Padua in Italy, their whole fund, they're investigating so much about gallium nitride technology reliability. And then you have the carbon nanotubes, and they're used as VIAS and ULSI technologies, but the challenge is high contact resistance and damage to any of the carbon nanotubes. So, and then you have the IoT devices, small form factor IoT modules, integration for sensors, computing, connectivity devices, but challenges are MEMS, high speed level ESD stress near IC pins. These MEMS devices could very well be solved by the polymer technology that I mentioned about. So there's a whole area that people still, the reason people don't do all this research so much is because they're fighting ESD fires every day. They don't have time to look at that. That's why universities are more useful for this kind of future technology research. And there are lots of research opportunities that can take place with these advanced technologies, technology scaling, advanced packaging, novel technology, testing accuracy. So when you make the CDM levels so 100 volts, how to measure it, how to test it becomes also very, very difficult there. Because the arc that you're testing for, it has a lot of variation in resistance. So you have to put it in nitrogen to make sure you control the arc. And so you can see things are more complicated. Finally, I want to mention 1 minute is about machine learning. Then you have human learning is a lifelong process, and then you can teach people to understand. If you can teach human babies, you can teach machines also. If you teach a baby difference between a cat and a dog, now you showed 100 different cats. The baby knows those are all cats, the same way the dogs. So that's what human machine learning purpose is. You teach it so that it can learn by example and then understand this. Now, what is the reason for this? Is that you can use the machine learning for ESD analysis. Like you look at the design, you can design it using machine learning, or how the devices break down, or you can use a lot of these TLP data to put the data in clusters, so the machine tells you that group of measurements is nonsense, it's noise. This is because a contact error, it's a human error. And we are doing some of the work with the University of Texas. It does now. It looks very interesting. There is so many opportunities available for machine learning. So I hope that this gave you some idea. ESD is now mainly focused in these areas. We still need to get more into Latin America. And you can see even Australia is now looking into it. A lot of work being done in India as well, and Japan, of course, a lot of it, and then a lot of European countries. And there is the ESD Association. It has many different courses on certification, how to design, how to protect in a fab area. All those courses are available. You can just go to esda.org and it has all those things. So with that, I hope I gave you a full overview of ESD and how complicated it is. When we first started a Texas Instrument, there were only two of us who worked on ESD. There are now almost 40 different engineers working on ESD. So that's just one company. There are thousands of patents and publications on ESD. So it's a very fertile field. And so I want to thank you for your attention.
Okay, so wonderful talk. Thank you very much. So I think we have time for questions. So if there are any questions, so please go ahead.
Dr. Charvaka, can you hear me?
Okay, we have a question.
Dr. Charvaka, can you hear me?
Dr. Charvaka, for your talk. I think it's very specialized and detailed talk.
Yeah.
However, regarding the protection, DSC, you mentioned about the snapback.
Right.
So when the device is in that stage, that is a kind of a damaged device or still is good.
Okay. The way we design it is we wanted to go into snapback during ESD, but limit the thermal point where it gets damaged. So the design technique will use under ESD, it will conduct an in snapback without damage. So your basic question is the snapback does not damage the device. Only if the current goes high enough to start the leakage into unstable regions, then it causes. So we always make sure. That's the reason we characterize under TLP and we say, okay, this technology can handle 10 milliamps per micron device width. So now I know how big I can make the device to handle. That's a safe current, and that's how we design it safely. You need snapback to protect, but you don't want the snapback to damage. The same way with the SCR2. If you make it good design, it can handle 30 to 40 milliamps per micron. That's a lot of current for 1 micron by device. But if it latches up, it will mess up the whole circuit.
Dr. Charvaka, can you hear me?
Oh. Yes.
Can you recommend for the students and for my use inexpensive electrostatic field meters that I can connect to my multimeter? Dedicated meters are extremely expensive. If I can connect something to my multimeter, I hope to make it much less than $200 or $300. Is that possible?
Yes, it is possible. Would you please refer to the esda.org? And if you have questions like this, if you ask an open question, there are many experts of ESD control. I am in the ESD physics and design, but those people can recommend these things. Because
Excellent.
they do get these questions from a lot of different labs in the universities and so on. So they can answer you better, or please send me an email and I'll put you in the right contact who can give you this information.
And they might also have devices for a generation of test pulses so that I can verify my circuits?
Yes, those are expensive, those
Oh.
TLP, but you can always build a home system using transmission lines. Some people build that.
Excellent.
Okay. Otherwise,
Thank you
those
much.
are million. Yeah, those are
Yes.
$1 million. So
Yes. Thank you.
precise instruments. Yes. You had a question?
Well, yes, another is nowadays, in the production integrated circuits, how much of those circuits are protected by this method? All or some of them?
Or you're talking about the microprocessors or any of the IC chip?
Oh, yes.
Oh, they're completely protected.
Completely.
Well, yeah, you can protect, let's say there are some very ultra high speed interface pins at 110 or 220 gigabits per second, you may not be able to protect them to the full level, okay? Let's say your standard is 125 volts per CDM. Those pins might be only 50 volts. They can't go any, there might be just a few pins. So what you do is you tell the production people, these particular pins are very sensitive and they know how to control so that those pins are not damaged. Also, a system manufacturer, even though when you put it in system, there are tiny pulses that go in and damage these pins. So the system designer has to completely understand what is the problem with these interface pins. So those are a lot of different issues. That's the reason it's so complex and so many people are involved to making sure all the future technologies are protected for ESD.
So thank you very much again. Out, I'd like to the CCE. This is part. Yeah, like we have been between the CCE organizing committee and the IEEE association, and to give the certificate recognition for this wonderful. Thank you so much. And also some like souvenirs.
Thank you very much. Yeah, always we have to do this.
Yeah. Oh, okay. So thank you very much. So thank you all for being here, those online. So enjoy the rest of this series of conference.